let's apply what we have learned about uniform electric field in this example over here. So the figure below shows a uniform electric field. Well, if you see a pair of parallel plates which are arranged like in parallel and they are oppositely charged, one positive charge, one negative charge, like this situation over here, then what will happen is in between the positive and the negative plates, there will be an electric field being produced by this pair of parallel plates over here. And the electric field in this region over here should be constant. Means by at any point in the region, if you try to determine the electric field, you'll find that the electric field at any point in the region should have the same magnitude and direction with any other point in the region as well. So you pick point A, you pick point C, you pick point B, whatever point you pick, and you find the magnitude and direction of electric field, you find them all to be the same magnitude, the same direction. That's the meaning of uniform electric field. And again, a uniform electric field is produced by a pair of parallel plates which are oppositely charged. The parallel plates means by they are arranged parallel, oppositely charged means that one plate is positively charged, one plate is negatively charged. Okay, so you see that the potential will decrease along the electric field lines. That means by you see this electric field line in here is going to the right, and you see that the potential is decreasing as you move rightwards. From 0, it decreased to negative 250 volt, and it further decreased to negative 400 volt. Going along the electric field line, you'll find that the electric potential should decrease. Okay, so these dotted lines over here are called equipotential line. Means by any point on this dotted line here have the same potential. If you find the potential over here at this point, you'll find it to be 0 volt. If you find the potential at this point, you find it to be 0 volt. If you find the potential at this point, you find it to be 0 volt as well. Any point on this dotted line should have the same electric potential. That's why it's called an equipotential line. Equal potential line. So the line where every point has equal potential. Okay, so this line here is also another equipotential line of negative 250 volt. So any point on this dotted line should be negative 250 volt for their electric potential. Same for this line. This is an equipotential line showing that every point on this dotted line should be negative 400 volt. Okay, so now we have know clearly the arrangement over here. Let's try to look at the question. So the first question asks you to find the electric field strength of the uniform electric field. So they ask for this electric field in between the two parallel plates, what is its electric field strength? So to determine that, we know that this is a parallel plate, we cannot use kq over r squared. Kq over r squared is for electric field that is produced by a point charge. In this case, it is not produced by a point charge. Instead, it is produced by a pair of oppositely charged parallel plates. So definitely no kq over r squared over here. Okay, they also never put any charge in the electric field over here. If they don't put any charge in the electric field over here, we are not able to let the charge to experience any electric force. Okay, if you have a charge inside there and the charge experience a force, then what you can do is you can use E is equals to F divided by Q to reverse calculate the electric field. But in this case, it's not possible because there is no charge in the electric field and there's no charge, so there's no force experienced by any charge over here. Okay, so the one way you can determine the electric field over here is to determine it through the parallel plate equation. Okay, so if you know it's a uniform electric field produced by a parallel plate, you can use this equation over here to determine the magnitude of electric field. So it's E over delta V over D. Okay, so the E over here will be the magnitude of the uniform electric field. Okay, magnitude of uniform electric field. Okay, so the delta V here, we usually call it potential difference for delta V. But usually when we talk about potential difference, there's a final potential minus an initial potential, right? But in this case, there's no charge moving from initial position to final position. Okay, so technically it's not really relevant to say what is V final, what is V initial. Instead, for this situation here, what are we doing is we are taking any 2 points in the electric field and find the difference between the electric potential between that 2 points. Okay, so let's say for this situation here, if I take point B and C, then the delta V will be taking the high potential minus the low potential. Okay, so this is what I do to get delta V. Okay, just to tell you here that why this one must be high potential minus low potential is because the E over here is the magnitude of uniform electric field. So the E over here must be positive because it's a magnitude of a vector. Electric field is a vector, magnitude of a vector must always be positive. So if the left hand side of the equation must be positive, then that means the right hand side of the equation must be positive as well. So what we need to do is we need to make sure the delta V and the D are both positive so that we can generate positive answer for E. So delta V we always take high minus low in order to get a positive answer, and D is just a distance between the equipotential line of the 2 points. Distance between the equipotential lines of the 2 points. Equipotential line. Okay, so what are the 2 points that I mentioned over here? The 2 points is the point where we take the high potential minus the low potential. So high potential be from 1 point, high potential of 1 point minus the low potential of another point. That is how you get delta V. But for the D, you take the distance between the two equipotential lines. So let me give you an example here. So over here you have negative 250 volt and negative 400 volt for these two equipotential lines. So the distance between the two equipotential line here will be 20 cm. So this D here, you put in 20 cm to convert to meter, 0.20 meter. That's how you get D. Okay, delta V in this case, you take big minus small. Negative 250 is larger than negative 400. So you take negative 250 minus negative 400. That's how you get delta V. And if you do that, you are able to get the magnitude of uniform electric field. Technically, the E that you get is for this region over here, but you know that the whole region here have the same electric field. Therefore, you know, even though that you are obtaining an answer for this part of the electric field, you can generalize it to everywhere in between the two parallel plates. So this is how we are going to approach this question over here. So let's do our substitution. E will be equals to delta V. I'll be taking VC. High point is VB. High is VB minus VC. Then the distance, I'll just write it as D between B and C. Okay, so VB is negative 250 minus negative 400. It's always high potential minus low potential. So negative 250 is larger than negative 400. Sorry, take negative 250 minus negative 400. Then the distance is the distance between the two equipotential lines. You are not finding the distance from B to C. This is not the distance you're looking for. This is the distance you're looking for. The distance between the two equipotential lines. So this one you substitute in the distance, which is 0.20. If you put in everything into your calculator, I believe you get an answer of 750 volt per meter. Okay, if you want to write Newton per coulomb, that's fine as well. Okay, for electric field, you can express it in terms of volt per meter or even Newton per coulomb. Both are fine. Next, question B. They ask you to find the distance y over here. Distance y is over here. You know the potential difference between them can be obtained. So you can use back this formula over here. You can get your delta V. You know the E will be the same as the E over here. So you can reuse the 750. Put it here. Delta V, you use 0 minus negative 250. And the distance will be y. So we are going to use the same thing again. So this time will be E is equals to VA high, VB is low, divided by the distance between A and B. Okay, distance between equipotential line of A and B. So this one, you know the electric field strength will be 750. It's the same. Then VA minus VB, you take 0 minus negative 250. And the distance between A and B, the distance between the two equipotential line, you call it as Y. So once you do that, I believe you get that Y will be equals to 0.333 meter, which you can also convert it back to cm, 33.3 cm. Okay, so that is how you obtain the distance between the two equipotential line of point A and point B. Okay, next we move on to question C. Question C asks you to find the work done by the field. By the field means by work done electric when you move a charge of 12 microcoulomb from A to C. Okay, always remember when we are doing work done, find three things. Work done by what? Whether it's work done by external force or work done by electric force or electric field or electric charge. Okay, you have to determine whether it's work done by what? By external force or by electric force. And next is from where to where. Always determine these three important things before you start to calculate anything. Okay, so since this is work done by electric force, you know that the equation will be equals to negative delta U, which if you expand, you become negative Q delta V. So this is the charge that is moving. This is the charge that is moving from point A to C. Okay, it's not the charge that is producing the electric field or something. It's the charge that is moving from A to C. Okay, so this one again, this one is always final minus initial. Okay, if it involves motion of charge, it's always final minus initial. Okay, so let's go. So negative, then the charge is a positive 12 microcoulomb charge. Then if you are finding a potential difference, final minus initial, final is point C, initial it's point A. So if you continue with your substitution, plus 12 times 10 to the power of negative 6, VC it's negative 400, VA it's 0. So if you do your calculation, I believe you get an answer of 4.8 times 10 to the power of negative 3 joule. So this is the amount of work that is being done by the electric field to bring the charge from point C to point A. So now we see that this answer that we have obtained for the work done by electric field to bring a charge from point A to point C to be a positive answer. So if you're not sure whether the answer should be positive or negative, here is one way you can check whether the answer should be positive or negative. So the motion over here is from point A to point C. So the journey will be from here to here. Okay, the journey will be going in this direction. So if you have a charge going in this direction, you know that the displacement is in this direction. Okay, this is the direction of the displacement. Next, you have to determine the direction of force. Okay, this is a positive charge that is experiencing a force over here. So the direction of the force will be following the direction of the electric field. Because if it's a positive charge, force will have the same direction as field. If it's a negative charge, the force will have opposite direction to the field. So this is a positive charge. The direction of force should be the same as the direction of field. The direction of field is pointing to the right. So the direction of force is also pointing to the right. Force electric. Okay, if it's force external, it will be opposite direction. Okay, so they are looking for the work done by the electric field. So it's the work done by the electric force then. So the electric force is pointing in this direction, and the displacement is pointing in this direction. So if you calculate Fs cos theta, right, you know that this cos theta will result in a positive answer. Okay, so this will mean by you get a positive work done. Okay, if the angle is less than 90 degree, then if you resolve F, you find that F, the component of F is parallel to displacement, then you get positive work done. This you have to recall back to chapter 5 from last semester. Okay, so if you proceed to question D over here, where they ask for the work done by the electric field to bring a charge from C to B over here. So over here is again negative delta U. If it's work done by electric field, it's negative delta U. If it's work done by external force, it's positive delta U. Okay, again, you can change it to negative Q delta V and proceed to do your substitution. So this is a positive charge here. So positive 12 microcoulomb. Then the journey final minus initial. So you take B minus C. Always refer back to this final minus initial. Okay, so we continue. So this is negative 12 plus 12 times 10 to the power negative 6. VB it's negative 250 minus VC is negative 400. So if you perform the calculation, you get your answer to be negative 1.8 times 10 to the power of negative 3 joule. So this time, the work done by electric field here, it's a negative answer. So why is it a negative answer? Let's try to check whether it's true or not. So let me remove everything over here. And we see that the journey is from point C to point B. Point C to point B, the journey is in this direction. So the displacement will be in this direction over here. But we still know that throughout the journey, the charge will experience a electric force, and the electric force follow the direction of electric field. Okay, we still have another external force in the opposite direction. Right now, we are interested with the work done by electric field, so we are only interested with the electric force. We are not interested with the external force. So the electric force is pointing in this direction over here, whereas the displacement is happening in this direction over here. So now the angle is definitely greater than 90 degrees. So when you resolve, you'll find that you go in opposite direction. Okay, S which is parallel to F elect. So if you resolve, you get them to be in the same direction. S parallel to elect. Okay, so if the resolved component is parallel with the force, then you get a positive work done. If the resolved component is anti-parallel or opposite direction to the force, then you get negative work done. So this one is negative work done. Okay, so now you verify that the sign is correct, and this will be how you solve for the work done by the electric field. If they ask for the work done required, or the work needed, or the work to bring a charge, so in that case, they're asking for the work done by external force. Unless they state that it's work done by the field, or the work done by the charge, or work done by the electric force, unless they state something related to the electric field, electric charge, or electric force, only you do work done by electric. If they don't mention that, then what they're asking for will be work done by external force, which they usually write it as work done required, work done needed, or work to bring, things like that. Okay, so always need to be very clear whether you are finding the work done by electric force or work done by external force. And this is how you solve this question over here.